We value significance tests because they assign a numerical value to an event, and it lets us know how rare an event is if a null hypothesis is true. What we need to keep in mind, now that we've been practicing significance tests for a while, is that alpha is arbitrary. We talked about this at the beginning of this unit, and I just want to bring it up again. We are supposed to choose alpha beforehand, so we can't make the results in our favor, whether we're looking to reject the null hypothesis or not. But what you need to consider is that in like the alpha equal to 5% case, 0.051 and 0.049 really aren't that different, yet one would cause us to reject the null hypothesis and the other would not. Keep in mind that smaller p-values are stronger evidence against the null hypothesis, so regardless of what our alpha level is, we're looking for smaller p-values just so that we can be a little bit more confident in our results. Before carrying out a test, we also want to make sure that what we're testing is worth testing. As it says here, statistical significance is not the same as practical importance. So even if we have a result that we may qualify as statistically significant, what does that mean for the real world? Also, when we're looking at means especially, keep in mind that they're not resistant to outliers, and that's part of why we want to make sure we're checking those conditions, and we stress that so much. If symmetry and outliers are not checked ahead of time, we could make an error of one type or another in a significance test. Outliers could alone do it. It could make the p-value much smaller or much bigger than the overall trend of the data is trying to show us. So we always want to check those to make sure we're not making an error there. There are two specific types of error that you need to be able to identify when you are conducting tests, as we have been throughout this chapter and as we move forward into the next unit, chapter 13. A type 1 error is when we reject the null hypothesis when we shouldn't have. This is going to happen alpha % of the time. Whereas a type 2 error is when we do not reject the null hypothesis when we should have. Beta is going to be what we use to identify that percentage as, or how often a type 2 error will occur, and that's something that you're not going to have to calculate. However, alpha is the same alpha that you use as your significance level. This chart does a nice job of summarizing kind of the 4 scenarios we can find ourselves in after we've conducted a significance test. We could reject the null hypothesis, and it could be that we're making the correct decision in doing so, that the alternative is actually true. However, we could reject the null hypothesis, and it would be an error to do so. It's actually true that the null statement is valid, and it's possible that even when our mathematics is sound, even when we've checked our conditions and done the appropriate calculations, we've made an error in rejecting the null hypothesis. Similarly, we could fail to reject the null hypothesis. And if we do so, we're going to be correct when the null hypothesis is true, so we're not going to reject it, it is true. Or we could make an error when we actually should have rejected the null because it's actually the alternative that we are interested in. Let's take a look at a specific example and see how the different errors would shake out. Suppose we have a factory that produces cell phones. The proportion P of defective cell phones needs to be under a certain percentage, let's just say 2%, in order for the factory to avoid being shut down. Our null hypothesis would be that P is equal to 2%. The proportion of defective cell phones produced by this factory is 2%. The alternative would be that it's greater than 2%, because that would cause us to shut down the factory. A type 1 error in any situation is going to be that we reject the null when the null is true. In this specific scenario, that means we will claim to have sufficient evidence to suggest that the factory is producing more defective cell phones than the 2% benchmark that we're looking at. The consequences of this is that the factory is going to be shut down when it shouldn't have. The company is not going to make any money. People are going to lose their jobs. A type 2 error, on the other hand, is that we do not reject the null hypothesis when we should have. So the null is actually false and the alternative is true. So the company is making more defective cell phones than we think, and we let the company continue to run that factory. What this means is that really the weight of this is going to fall on the customer's shoulder. So more people are going to receive defective cell phones. Customers are going to be unhappy. You may have to, on the AP test, state what is a type 1 and what is a type 2 error given a certain situation, such as this one, and then also try to determine which one you think is more severe, which one's going to put you in a worse situation. A lot of that is up to interpretation. You can make an argument either way. What you want to do as someone taking the AP test or taking just our regular test at the end of this unit, even if you're not sure, you can see the pros and cons to each side. Pick a side, defend it. Don't waver back and forth between two of them. In this case, I would say that the type 1 error is a little bit more serious. Just because of the consequences for the company, they're not gonna have the opportunity to make any money whatsoever. Whereas the type 2 error, they might lose some customers, depending on how bad the company really is, how the proportion of defective cell phones that they're actually producing, could make for more and more unhappy customers. But I think the type 1 is going to be more serious in this situation. Of course, sometimes that's up to interpretation and it can be argued, but just make sure, again, you take a clear stance, pick one side, and defend it. Some of you have already made the argument for the p-value that even though it's an unlikely scenario, say you get a p-value of 3%, there's still a chance that that scenario could happen. And maybe the soda cans are not being underfilled, or the company is not producing too many defective cell phones. And unfortunately, that is what happens with hypothesis testing. We set this alpha level, and when we are below that alpha level and we reject the null hypothesis, saying there's evidence for the alternative, there is a chance we're wrong because there is a chance that this phenomenon occurred. Almost nothing is impossible. So even though it has a small chance, there is a chance. So you want to acknowledge that when you're doing these tests as well. And it will be whatever the significance level is, that's going to be the probability that you're making this type 1 error. As we've already stated, a type 2 frequency, we're going to use beta for our symbol. You need to recognize beta as being a type 2 error frequency. It's not easy to calculate. You will never have to calculate it. Statistical software can do that for us. Don't worry about having to come up with it on your own, but you will need to know a little bit more about beta in relationship to the table we looked at earlier. In addition to understanding type 1 and type 2 errors, we also want to talk about something called the power of a test. It's common to report the probability that a test does reject the null hypothesis when the alternative is true. So that would be making a correct decision. We've rejected the null, we've suggested that there's evidence that the null hypothesis is inaccurate and the alternative is really what's going on with this phenomenon. This is called the power of the test because usually we want to reject the claim. It's the exact opposite of a type 2 error, and so its probability is 1 minus beta. So let's take a look at this table and kind of fill in some of these probabilities. A type 1 error, where we reject the null when the null is true, will happen alpha percent of the time. Usually this is going to be a small probability because even though we're stating that the probability that this event occurred is small, there's still the chance that it could happen. The type 2 error we've identified as beta. which you're not going to calculate, but you may be given beta. And something you might have to do with that is, say, state the power of the test. So again, the power of the test is going to be when we reject the null hypothesis when we should have. We've made the correct decision. So here we'll have 1 minus beta as the probability that that occurs. And again, that's power. You may be asked specifically about how to increase the power of a test or how to calculate the power of the test if you're given different alpha and beta values. Similarly, we're going to make the correct decision 1 minus alpha percent of the time if we fail to reject the null hypothesis when the null was true. I strongly recommend that this chart is something you study with for the AP test and for your upcoming test on this unit. I think it ties together a lot of the ideas from this error section. With confidence intervals, we often looked at how we could narrow the margin of error or the width of the confidence interval to get a more precise estimate. When it comes to hypothesis testing, we want to increase the power. A high power is desirable because that's the likelihood that we're not going to make a type 2 error, but we're still able to reject the null hypothesis, which is usually what we're setting out to do. 80% is considered standard. So thinking about the fact that 80% is 1 minus beta, we want a beta value that is less than 20%. If the power of our test is too small and we want to think about how we can increase it, there are several different ways we can do so, and they all have pros and cons. One is to increase alpha. Another is to consider a different alternative hypothesis, one-sided versus two-sided, depending on the scenario. We could increase our sample size. We could also decrease our standard deviation. If we increase our alpha value, our significance level, we're going to increase the probability that we reject the null hypothesis because our rejection region is getting bigger. However, this is also going to increase the probability that we make a type 1 error. So it's not always desirable to increase alpha, but it is one way to increase the power. Another option is to increase our sample size. As we've looked at with confidence intervals, increasing our sample size will decrease our standard error. In turn, increasing the test statistic, it'll pull our p-value further along the tail. With that smaller probability, we're going to have stronger evidence to reject the null, so we have a higher power. Decreasing the standard deviation, whether it be sigma or S or the standard deviation of the proportion, that's going to have the same impact as increasing our n value. So these second two really kind of go together. And again, all three of these are going to increase the power of our test, which is desirable in general, even though some of these individual pieces are not as desirable as others. Increasing the alpha level, not always great. Increasing our sample size is probably our best option. Decreasing the standard deviation isn't always possible. Choosing a two-sided versus a one-sided alternative is going to take the same alpha value, so say we have an alpha value of 5%, and it's going to split that into the two tails. So instead of having 5% on one side of your curve, you're looking at 2.5% on either side. This decreases not the rejection region as a whole, but it decreases the rejection region on one end. So it has almost the opposite effect of increasing alpha. Be prepared to talk about how you can increase the power of the test even though you can't calculate the power specifically, since you're not necessarily going to be able to calculate beta specifically.